Let's talk about some problems, but really there are characteristics in the development of the core of the node, which fundamentally have to do with the architecture of the system, which was written in Rust. Many define it as the JS node of C. Whether it's written in Rust or C, at the end it produces a binary. The language doesn't matter. What we wanted to not link, given that we chose an almost internal language, in reality we didn't want that the choice of the language it had an influence on the choice of the language of the smart contract. Otherwise we would have closed ourselves in an even smaller world, not loved by the masses, but loved by a tiny minority that have given it their heart and soul. So the problem is how to write the smart contract. Clearly, in the world of the smart contract, this is the most important study we've done within the blockchain, seeing what the others have done, because you don't want to invent anything in this world unless you're improving things or making them more efficient. So we noted that almost everywhere people had invented their own language for programming. This seemed a bit mad, so we understood why. Why have they done this? The main motive is that creating an own language which is not potentially deterministic, there's a way of driving the blockchain wild. So if this is a transaction, let's say, imagine this is the hash of a database before and after a transaction. If this is time X, this produces a delta dB. So it takes inside a piece of information, it cancels, it modifies, or it writes, and the database, which was in one way before the transaction, and now it's another way after the transaction. To make a blockchain in general, it's necessary that this delta dB is deterministic. Because otherwise, if it wasn't deterministic, if there's a way of making it non-deterministic, this Tx here would create differences in databases here, here, and here. From now on, there are 3 nodes that cannot be synchronized. So how can we impede that this happens? That there's a non-deterministic delta. In reality, it's easier to think about how we can break the blockchain. You break the blockchain, saving a random value, saving a float in the database, saving in the database a hash map, saving in the database a time. This is a way of driving a blockchain mad. With this, if I save a random value on 3 databases, I'll have 3 different values. The hashes will all be different. The float won't necessarily give this problem, but I have different machines. They're all going to do rounding. The hash map utilizes random numbers. The hash map is a data structure in which the key is the hash of the value. So it is very easy to make a research within the hash map differently to a vector, because a vector with 300 results, if I go look inside for the key, I have to keep looking until I find that key, because maybe the key is a whole number. If I as a key support hash, if I use the hash of the value to set the key, when I go and do a search to find that value, I find the hash straight away and I can manage to find what's there. So it's as if with one attempt, without looking at everything, it's either there or it's not there. So even if making the hash is complex in technical terms, it's straightforward in computational terms. Since these hashes are not the hashes we've seen before, but they're internal hashes, native hashes, which maybe deal with 2 or 3 characters, not 32. The problem is that these characters, there may be conflicts. How do we solve these conflicts in the hash map? We solve this by creating an internal system in which the hash map, if there are no conflicts, saves the direct value. If there are conflicts, it saves a vector of values. I have to save chow. I have to make a hash of chow, not the hash with SHA-254. Let's say the hash can return only 2 values. There are only 2 numbers. So I can either 04 of the hash of chow. At the position of 04, I save chow. And meow also has a hash of 04 because the 2 numbers, the conflicts are very high. So in this case, I cancel chow. I transform 04 into a vector of chow and meow. Clearly, in that case, to have the value chow, I must arrive immediately at 04, and then I must iterate a vector of 2 or 3 elements, which is much more efficient than iterating 300 or 400 elements. They realized that those who make hash maps, they do them for reasons of performance. So having a slow hash map sometimes can compromise the software, and some sick person realized that it's possible to make hash map attacks. So there being just a few possible values with 2 characters, only 99, you can force the system, saving data which always produce the same hash. So you can slow the system, weakening it, and this has been done on routers. This is a story, you could make a Netflix series about it, because the hash maps were used within the router for the research of IP addresses to be banned. So if I put the blacklist into a hash map, what happens? The hash map has limited dimensions. Its cache is small, and they deliberately continued to send IP addresses which generated the same hash. So forcing the hash map to become a vector and scroll through all the data, and this gave them a few microseconds to make the attack. So how did they fix the problem of the hash map attacks? The hash maps now have a random value of initialization. So you no longer put the hash map of chow, but when you begin the hash map, it inserts a random value which becomes the prefix to make the hash. So you can't forecast what the key that will be used will be in this case. If you save a hash map as it is within the database, you can run into the problem of non-determinism. This is the reason why nearly all blockchains have decided to write their own languages, which is an alias language of another language, but the compilers have a smaller subset of information, given that there's no need to put in a REST service or anything else within the smart contract. It's only a computational logic of how the data flows. And so many have chosen to write their own language and to voluntarily impede that there is random and a series of things. We've made a different choice. Our choice is this. We've chosen WebAssembly. WebAssembly is a language, a compiled language, the output of a compilation, which nevertheless comes from a series of languages which can be Rust, Java, C, C++, Python, etc. There are many languages that can compile, and it's not transpilling like TypeScript does. But it's a compilation. It makes a binary code and technically intercepts with the WAS machine all those effects of random and hash map and anything else. So you can happily put in a random value. What happens? A strange thing happens. It always gives the same value. Why? Only if you write rand. There's a way of having different values, but given that today the random values don't exist, there are pseudo-randoms that start from a seed, and the binary code, not having the chance to voluntarily communicate externally, it's as if every time it sets off from the same conditions. And as it can't save anything because it's ephemeral, every time it starts, if it calls up random, it will always give the same value for all the smart contracts that we launch. This has allowed us not to remove random and not to have to alter a programming language. We have introduced random host functions which give you a random value that you need to carry out your operations. Clearly, it's a deterministic random value which is taken forward on all the nodes in the same way. So you can't predict it because it has taken into account the hash of the block of the last transaction. So afterwards, say after 10 passages, you can't know what the new random will be. So it's a pseudo-random, and it conserves the characteristics of a pseudo-random. But this was exactly the objective we wanted to achieve. But the objective we had given ourselves was this. Given 3 nodes, Tx runs here, and here, and here. These 3 nodes are running now, and this function does a random. And on the basis of the choice of the random, if it's greater than 0.5, take the right branch of the function, otherwise take the left one, creating 2 different outputs of the application. What we wanted was that when this was launched, in this moment, all had the same random value. The problem is the concept of in this moment, because we know that the transactions can move asynchronously, so there is no internal time, but there's a seed which evolves every time the random function is called, independently of the time. This gives us the guarantee that if now, at this moment, the random gives us 0.4, for example, and we're at the 10,324th transaction in block number 23. If I start from the top and make all the transactions from the beginning and arrive at this transaction in this block 23, the new random will be 0.4. This is something we wanted. It's not a chance. You'll see the last aspect better in the next lesson. I'll remind you that the was machine, which is the machine that runs the smart contracts, has a memory. This memory can be accessed by the smart contract, which uses this memory, or the core. The core directly uses this memory. The problem is that to talk to this memory, you can only use whole numbers. We faced this yesterday. There are other cases where this happens. It's not a defect of the system. It's a best practice which gives excellent results. But the problem is, if I have a core that needs to evoke the smart contract with the PIPO method, which sends "how are you?" there's no way to send a string with the PIPO method. So what does the system do? It takes, in theory, it would be enough to take the PIPO variable and put it inside the memory here and have an offset of whole numbers and a len of whole numbers to pass to the smart contract these 2 items of data, and the smart contract from inside goes and fetches, according to the offset and according to the length, the byte array of the variable. But we realized that this trick worked only with integers, strings, and simple structures. If we talked about arrays and objects, the system within the memory began to use pointers and efficiency systems. What does this mean? It means that if I put the word chow and then I create a vector of the word chow and meow, one is a pointer to the outside. What do I pass within? I have to send more than one element. I can't just send the beginning and the end. I have to say where all the variables are and create a greater traffic than what's required. So what did we decide to do? We decided to create a system that's very similar to Esperanto for some aspects. The phrase, the parameters that serve to send a string or a group of parameters are serialized in a message pack. What does this do? This produces a byte array. So even if there were pointers, external references, or whatever else, when you create this, it's collapsed into a self-consistent structure. So a vector or a structure is collapsed into a vector of bytes. The vector is put in the memory, and we have the certainty to not have to pay attention to the fact that the data was anchored to a pointer, or even if some languages like Rust have data about the ownership of the data within the pointer, as you can't take the data if it's under the control of another resource. So, in this way, serializing everything, you collapse everything, it's taken inside. At that point, the smart contract receives the offset and the length. The function of the smart contract is to take care via a utility that we have made to collect from the memory this data, deserialize it, and get the arguments inside itself. This is an important concept for the next lessons because, for instance, when you have to set a variable and put it in the memory, which may seem to be an anomalous step, we do this so as to avoid an external problem. That is, how do we get the data outside the smart contract? This is the same problem as before. If I have to send a function to the smart contract without parameters, I will never receive an answer of true or false, because these are not integers. What do? I take the smart contract, put the data serialized in the message pack in the memory, and return two numbers. One is the offset, the other is the length. And then it's the core that with automated routines takes the data. The strangest thing that you can see in the SDK is that if you create the log function, everybody would write it like log MSG. But if you go and look in the SDK, you'll see log integer A, integer B. This is the log. Because effectively, the log needs two whole numbers to work. Integer A is the offset of where the variable is, and integer B is the length of what has to be done. So the log goes into the memory, it collects the buffer, it transforms it in from buffer into text on the basis of the length, which is written in B, and so it creates an output of what it finds there.